So we're told that potassium dichromate is formed when nitric acid is slowly added to a potassium chromate solution. The chromate ions, as you can see, these are the chromate ions there in the solution. They reach equilibrium with the dichromate ions. So these ones here are the chromate ions. Maybe we can just write it here. Chromate. Okay, chromate ions. And then this one here, these ones are the dichromate ions. Dichromate ions. Define the term chemical equilibrium. How do we define chemical equilibrium, guys? It is when the rate of the forward reaction, equals the rate of the reverse reaction, equals the rate of the reverse reaction. Okay, so that is it there, guys. Very nice. And then 6.2.1 says now they add a concentrated nitric acid solution to this mixture. Now guys, when they're saying they're adding a concentrated nitric acid, the moment you should already think of what is nitric acid. Remember, nitric acid is HNO3. Now HNO3, when it dissolves in solution, becomes H plus and NO3 minus. That is the first thing you should think of. HNO3, it separates into H plus and NO3 minus. Now good people, how does that help you? That helps remind you that because you have H plus and NO3 minus being added into the solution, you should already look at what you have here, what might be increased by adding HNO3. So the thing is, guys, you're gonna increase H plus because it is the one that is here, you see. So that means the concentration of H plus is gonna increase. Now if the concentration of H plus increase, you added H plus, what will the system do? The system is going to say, no, you're not going to increase H plus on my watch. I'm going to favor a reaction that will reduce this H plus. And which reaction is that? Is the forward reaction. That is the one that is going to reduce H plus. So therefore, the solution is going to become what? They say, what color change will be observed? Choose from more yellow to more orange. Well, the answer will be more orange, because we will have favored the forward reaction. Now explain your answer. So here it's more orange. Now they want you to explain the answer in terms of Le Chatelier's principle. Using Le Chatelier's principle, you have to tell them that tell them the effect. Adding HNO3, right, increases what? It increases H plus ions in the solution. If this increases H plus ions, how will the system respond? So the system will favor the forward reaction. It will favor the forward reaction to counteract the disturbance, you understand? And then since it's gonna favor the forward reaction, therefore the concentration of CrO42 minus, which is this reactant here, and also the concentration of H plus ions will decrease while the concentration of the products will increase. The concentration of the products will increase, causing the solution to be more yellow. Not more yellow, more orange. Okay, so that's what you have there. That's what you have, guys. So when you add HNO3, you are increasing the H plus ions, which is going to favor the forward reaction because the system will want to reduce H plus ions, and therefore now that means the yellow chromate ions are going to decrease, and then the orange chromate ions, which are the products, are going to increase. Therefore the solution is going to become more yellow. Are we all happy with this? Are we clear? Let's listen to what the question said. The question said when the temperature of the original reaction is increased. So what did they do? The fact is that they increased temperature. So that is the first thing we need to look at. The temperature was increased, right? Let's already remember that when you increase temperature, an increase in temperature favors which reaction? It favors the endothermic reaction. Alright? An increase in temperature favors the endothermic reaction. I remember we used to use the acronym INTEND. INTEND. Increase in temperature favors the endothermic reaction. INTEND. Ne? Increase in temperature favors the endothermic reaction. So that's what we must know, that endo, remember, it's cold. Exo, it's hot. So when you increase temperature, you can't choose exo because it will be more hot. The system will choose endo, the one that is cold. Okay, so we already know here that now the endothermic reaction is favored here. Let's already know that the endothermic reaction is favored due to an increase in temperature. Endothermic reaction is favored. You know what? At 6.3.2 there, I'm not going to answer 6.1.1. I'm going to answer 6.3.2 first by already explaining. Okay. So what we observed is that, so what you should write first is that an increase in temperature favors the endothermic reaction. It favors the endothermic reaction. Okay, an increase in temperature favors the endothermic reaction. Now, what are we also told? We are told that it is observed that the color of the mixture, it changed to yellow. The color of the mixture changed to yellow when we increased temperature. Listen to that. The color of the mixture, it turned yellow when we increase temperature. The color turns yellow. If it turns yellow, that means the reverse reaction was favored. Right? The observation of seeing yellow there tells us that it is the reverse reaction that was favored. And if it is the reverse reaction that was favored, so that's what we write here. The solution turned yellow, or the mixture turned yellow, suggesting that the reverse reaction was favored. This suggests that the reverse reaction was favored. The reverse reaction was favored. Now, since the reverse reaction was favored, then that means the reverse reaction is what? That means the reverse reaction is endo, because the system favors the endothermic reaction. So since the reverse reaction was the one that was favored, it means the reverse reaction is endothermic. Reverse reaction is endothermic. Okay? If the reverse reaction is endothermic, that means therefore the forward reaction is what? The forward reaction is exothermic. Guys, from my explanation here, it should answer 6.1. It says, is the forward reaction endothermic or exothermic? So I simply write that it's exothermic. You see, that's why you can answer the question that explains first, so that you logically explain why you think that, what is happening, and then you can answer that question afterwards. Is fine. So good people, please, I hope that it's clear on especially the one here for temperature. This is how we always answer the ones about temperature. When you must see from the diagram, ne, to say you must see, the diagram must tell you that this reaction was favored. Then when you must remember, if there is an increase of temperature, the endothermic is the one that is favored. If there is a decrease in temperature, the exothermic is the one that is favored. So when I just gonna match that description with the one that was favored in the reaction there, the reaction that was favored, and therefore you will be able to tell whether it's endothermic or exothermic. You are like a detective. So like a detective, you check, if they're saying the solution turns more yellow, it means this reaction here was favored. If the solution turns more orange, it means the forward was favored. That is how it is. So since it turned more yellow, right, it means the reverse was favored. And if the reverse was favored, that means the reverse should be endo, because temperature was increased. An increase in temperature only favors the endo. So since the reverse was favored, it means the reverse must be endo. Therefore, that will make the forward to be exo. You see the logic there. That's how we answer it. So first of all, they say to us that, okay, we're working with Cr2O4. So we just have to write it here that we're working with Cr O4 2 minus in aqueous solution. Then we have H plus in aqueous solution. Then we have Cr2O7 2 minus in aqueous solution. And then we have H2O, which is a liquid. Now the ratios rise. So this is going to be equilibrium mole. This is going to be equilibrium concentration. But this one is going to be initial mole. Now, the ratio there is 2 is to 2. Then you have 1 and 1. Looking at these numbers here. Okay, so it's 2, 2, 1, 1. Now, the initial mole now, we were told that we had 11 moles of CrO4 minus. So you had 11 here initially. Oh, guys, by the way, we can already fill in the change table, ne? By change row. So, because here it's 2, guys, we're going to say minus 2x because it's a reactant, it gets used up. We also say minus 2x. We say plus x, we say plus x. Now that we have filled up our change row, we can then say initial moles of this was 11, so we put 11 here, and then for H plus we had x. And then oh guys, now I cannot be using x because we also have x there, so that means we're supposed to use y, ne? Just like we're doing on our last session. But it's fine, guys. I know we can just work on it, but actually let's use y so that we don't get confused. But I'm quickly gonna say, okay, I'm quickly gonna use y now. So I'll say minus 2y minus 2y and then plus a y plus a y. Now we're told that at equilibrium we have 9 mole per decimeter cubed of Cr2O7, meaning for this one, what are we given? What is this thing? You must know how to you must know the units, guys. This is concentration there. So since it is at equilibrium, it's called equilibrium concentration. Okay, it's equilibrium concentration, which means that we are given for this part, we are given this part 9, because that is the equilibrium concentration. Okay, so now how do we work on this? How do we get the answers when we don't have so much info? Well, remember, for the products we start with 0 and 0. That's what you should remember. So now what do we do now? Because remember, we need a row of ice. We need some ice blocks. We need a row of ice. If we can have maybe this part with information, meaning this part, if we have information, we can solve for y. Even here, if we had, we could try, and then there we could try. But then now, we don't have anything on the equilibrium mole row. So now what do we do? What do you think we're gonna do there? To get our ice block here, at least we need to get, since we're already given some information about equilibrium, we need to change this equilibrium concentration to equilibrium moles. Then we can have our ice block. You see, then we can solve for y. So how do we change concentration to number of moles? Now remember, the formula that we can use is this one. We could say concentration is equals to N over V. Now the concentration that we're given is 9 mole per decimeter cubed. Now we need the number of moles. What is the volume? Remember, we're working in a 0.5 decimeter cubed volume. Okay, so we use that volume there, 0.5. And please check out, sometimes they might give you centimeter cubed there. You must divide it by I think 1,000. Yeah, by 1,000. So now therefore this means that the number of moles of that Cr2O7 2 minus is gonna be 9 times 0.5, which I believe is going to be 4.5 moles. Now since we have 4.5 moles, where do we write that? We write it here. We say 4.5 moles. These were the equilibrium moles. Okay, this is the equilibrium concentration, this is the equilibrium moles. Now we can get y. So when you write our ice block, we say 0 plus y give us 4.5. So therefore our y is 4.5. Okay, therefore our y is 4.5. So we're gonna put here 4.5. Our y is 4.5. That means even here we have 4.5 here, right? So we're gonna put 4.5, and then here we're gonna say minus 2 times 4.5, that gives you minus 9, right? Same thing here, minus 2 times 4.5, that gives you what? Minus 9. Then good people can start filling in. 11 minus 9 gives you 2, and then x minus 9 gives you x minus 9. Then remember, for equilibrium concentration, you say these number of moles, you divide them by the volume, which is 0.5. Now the answer here is gonna be 4. Okay, it's gonna be 4. And then here you're gonna have x minus 9 over 0.5. Good people, this is what we have so far, right? So what are they looking for there? They are looking for the initial moles of H plus that is in the container, right? They said if the equilibrium constant is 0.9. Guys, what is the equilibrium constant? It's your Kc. So you see, they didn't want to tell you that Kc is 0.09. They said equilibrium constant. Please guys, these are the terms that the examiner uses to make sure that not all of you get the question correct. You see, so please, equilibrium constant is Kc. So we already have our Kc. We can go to this equation here. So we can say Kc is equals to the concentration of Cr2O7 2 minus, and then the exponent is gonna be this ratio there, which is 1. And then same thing for H2O, the exponent is gonna be 1. And then for Cr2O4, the exponent there is gonna be, the exponent is gonna be 2. Okay, and then for the concentration of H plus, the exponent there is gonna be 2. Okay, So Kc, how much is it? We have 0.09. And then the chromium ions, what is the equilibrium concentration? It's 4. So we put 4 there. What about the concentration of H2O? Guys, remember that for H2O it's a liquid. So the concentration we just put 1. Okay, so we're just gonna put 1. Remember, solids and liquids, the concentration we just put 1. And then for Cr2O4 2 minus, which is this one here, the concentration. Oh, I made a mistake. You see, these things are a bit confusing. 207 2 minus is this one, guys. Ne? It's 9. Sorry for that. So I was supposed to put 9 here. It's 9. And then this one, the 2 minus, is the one that is 4. Okay, so we put 4 there, then we say squared. Then we say for H plus we don't have, we actually have x minus 9 over 0.5. Okay, so don't forget to put squared here. Okay, then now we can solve for x. Remember, guys, I told you that already by doing this you already have your 7 marks. Getting x is the last mark. Okay, you already have your 7 marks here. So yeah, just getting x is there. I know, guys, you know how to get x here, ne? But let's do it. So cross multiply. 9 is equal to 0.09 times by this thing, 4 squared times by this thing, which is the x minus 9 over 0.5 all squared. Then you divide by 0.09 4 squared. Then you divide by 0.09 4 squared. So this cancels that cancels that. Then you end up with x minus 9 all over 0.5 all squared, and then you'll have 9 all over 0.09 and then 4 squared. Then, guys, you take a square root here, square root here. Then you take then you're gonna have x minus 9 all over 0.5, and then you're gonna have 9 0.09, and then you say 4 squared. Right, now you then multiply both sides by 0.5. Yeah, guys, it's a lot of maths here, eh? You know, guys, some of us, we are not good in maths, eh? So this is what you have. And then now your x, now you put 9 to the left, so you'll have 0.5 times the root of 9 all over 0.09 times by 16, as this 4 squared, and then you say plus 9. So, guys, therefore your x will be what? So the answer is 10.25 moles. So these are the initial moles of that thing. They are the initial moles of the H plus ions that were there. They were 10.25 moles. I hope that was clear, guys. Very good. I hope that is okay. So the more you do these questions, guys, the more you realize that these things are actually quite easy, ne? So if you just use this method that I taught you, you are guaranteed to have your 8 to 10 marks. You are guaranteed. But make sure you also do there are these other questions, right? That's why I want us to talk about graphs. So let's talk about graphs, guys, before we divorce each other for today. When we discuss graphs, these graphs are just the factors. They are graphs of the factors that affect concentration, that affect equilibrium. Remember, we talked about Cape Town, which is concentration, pressure, and temperature. So we want to see how does this thing happen. How do we tell whether it was concentration or what that was changed, ne? So let's do this. So we have two main graphs that we're gonna be discussing. we have the rate versus time graph, and then we have the concentration versus time graph. Now you need to know how to interpret them, okay? The rate graphs, the reaction rate graphs, are going to be talking about the forward reaction and the reverse reaction. Okay, so let's understand that the reaction rate graphs are going to be talking about the forward reaction and the reverse reaction. Okay, that is the rate graphs. And as you can see, the forward reaction is usually represented starting there, and then reverse starts here, because the reverse it starts from 0, because I can remember the reverse is when the products are making back the reactants, so they don't just start by doing that. That's why so that reaction starts by not happening at all, because we said here for products we put 0 because the products are not there initially. So that's what they're trying to tell you, that initially it's only reactants that are present, and then the rate of the forward reaction is high, as you can see, because initially it's only reactants that are present. It's only reactants that are present, but then the products are not present. That's why the rate is 0. Products are not present. Okay, so with time, however, as reactants are being used up, then you start to see the reaction, the reverse reaction increasing, you see, and the forward reaction decreasing. And then as the products are formed, now the rate of the reverse reaction, it increased from 0, as you can see here. Now at equilibrium, the rate of the forward reaction equals the rate of the reverse, as you can see here. The rate of the forward will be equal to the rate of the reverse at equilibrium. So it means that these reactions are going to be at the same speed. So remember that it is a dynamic equilibrium. Like we said, it's a dynamic equilibrium because the forward reaction is still occurring and the reverse reaction is still occurring. So it's a dynamic equilibrium, just that they are happening at the same rate. So hence the rate graphs should indicate that both the forward and the reverse rates are equal. So you must show these, guys. You must show this type of graph to show that what is happening at the start, at the beginning, and then what is happening upon reaching equilibrium. So I don't know if I can just maybe try to just simply highlight to say, let's see. Let me just remove here. I just want to highlight something so that we understand. So please understand that here at this part here, at this part here, this is before reaching equilibrium. This is before reaching equilibrium. Okay, but then this part here, let me take my highlighter again. This part here, this, it's when we have reached equilibrium. Here equilibrium is reached, has been reached. Okay, equilibrium has been reached. I hope we are okay so far. Now, why am I highlighting this? I'm highlighting it because once we have reached equilibrium, people decide to then mess with the equilibrium. You know, they decide to add some stuff or remove some stuff. That upsets the equilibrium. And now when it upsets the equilibrium is going to favor the reaction that is going to counteract whatever disturbance is there. So which means that there is going to be a disturbance here. Once you disturb equilibrium, therefore the system must, according to Le Chatelier's principle, the system will reinstate a new equilibrium. Please, you remember when we were talking about Le Chatelier, I want to give you to take you back to the definition of Le Chatelier. Yo, I just saw it now, guys. You saw it? Yeah, here. We said Le Chatelier's principle says when the system is disturbed, the system will reinstate a new equilibrium. This was quite an important statement, that it will reinstate a new equilibrium. How? By favoring a reaction that will oppose the disturbance. Okay, so if the system is gonna reinstate a new equilibrium, how does it achieve this? How does it reinstate a new equilibrium? What does it mean to reinstate a new equilibrium? Well, that's quite simple. To reinstate a new equilibrium means to have another equilibrium. Okay, so let's just show you diagrammatically. Yeah, if I have my graph drawn here, let's just draw it with a black pen. So if I draw my graph here like this, and then I draw my graph here like this, right? I'm gonna say we started here. This is the forward reaction. This is the reverse reaction, right? This is the forward, and then this one is the reverse. And then here I have reached what? Equilibrium. But you know what I'm gonna call it? I'm gonna call it equilibrium number 1. Why am I calling it equilibrium number 1? Because I understand that we might disturb this system, and then therefore it's gonna form another equilibrium. So how do you disturb the system? Right, let's say you have A plus B forming C plus D. What is to disturb the system? Right, you can disturb the system by either increasing or decreasing concentration, by either increasing or decreasing pressure or volume, right, or by increasing or decreasing temperature. That is how you can disturb the system. That's how you can disturb the equilibrium. Alright, that is how you can disturb the equilibrium. So now, if you disturb the equilibrium, how is it going to look like on the graph? So let's understand so I'm gonna show you. We're gonna start with concentration. We're gonna start with concentration, increasing or decreasing concentration. So let's look at what happens if you change concentration. Let's see how the reaction rate time graphs are gonna look like. Remember that the reaction rate time graphs show the forward and the reverse reactions. So here you are. Here is a spike here. What does this spike, this sudden spike, what does it tell you? This means that you added something. This spike here tells you that what did you do? You added something. So here the example that they have is that let's say we add more NO2 gas. If you pump in more NO2 gas, what is going to happen? Look at this. The forward reaction, it spikes. It spikes up. Why does it spike up? That tells you that it's spiking up like that because it's trying to what? It's trying to say to you that we're favoring the forward reaction rapidly, very fast. You understand? So if NO2 is added, the forward reaction suddenly increase. The forward reaction will suddenly increase, shown by the spike. Shown by the spike. So this tells you that the forward reaction immediately, it increased very fast so that it can use up the NO2 that you put inside, right? Then after it does that, it gradually then slows down. And as it slows down, the reverse reaction also now starts to increase. You understand? So it's also start to increase there so that they can reach a new what? A new equilibrium. So guys, this is what I call equilibrium number 2. Equilibrium number 2. That's the second equilibrium. Remember, this one was equilibrium number 1. You see, so you can have more than infinite number of equilibriums as long as you are disturbing the system. You understand? So understand that that spike there is just the system telling you that come on, forward direction, start working, start doing your job. You understand? So it does it very, very fast because you also added this NO2 very fast. When you add something, it's like, here you are, here's the thing here. It immediately goes into the system. You understand? So concentration, as you can see, so this is what we call a change in concentration and how it affects the rate graphs. Okay, you're gonna see a sudden spike in that reaction rate graph. And then what if you remove this? If you remove this, you see a sudden drop in one of the reaction rate. Are you able to see that? So what is happening is that at T1 there, at T1, Angela, we had reached equilibrium already. So at T1, NO2 was removed. NO2 was removed. If you remove this NO2, right, that means that which reaction is going to be favored? Because you removed NO2, the reaction that will be favored is the one that is going to increase NO2, which is the what? Which is the reverse. You understand? So we're going to favor the reverse reaction. So that is why the forward reaction decreases sharply. You see? So the forward reaction decreases sharply. Decreases sharply. Okay? So guys, I hope that you can see that a spike indicates a change in concentration. Alright? A spike tells you that there was a change in concentration. So the forward direction immediately goes down, and then now it starts to increase again, same as the reverse, so that they reach another equilibrium there. I hope that is clear. I hope it's clear in terms of how concentration affects the rate graphs. So here we have a change in temperature. A change in temperature is going to cause a gradual change. Do you see now how it's different from concentration? A concentration forms a spike. It forms a spike, but here it forms a gradual change. Temperature is a gradual change. That's how you know that the factor that was changed is temperature. Because they are going to ask you guys, they are going to give you a graph with many equilibriums, and then they're going to ask you which factor was changed here, which factor was changed there, which factor was changed. So please, I already told you that you are going to see that these ones are not the ones I wanted us to discuss, sorry. So guys, a change in temperature, no, the gradual thinking is actually it applies to another type of graphs. Here we're just discussing reaction rate graphs. When I'm saying reaction rate, I want you to think of forward reaction and reverse reaction. Okay, that is reaction rate graphs. You must always check on the y-axis or what you have on the y-axis. If you have reaction rate, already think about forward reaction, already think about reverse reaction. Okay, so now what we see here is that if we increase temperature, remember, increase in temperature, it's gonna favor the endothermic reaction. Increase in temperature is going to favor the endothermic reaction. So here is what we have. We have reached equilibrium again. Then there was a sudden change here. I want you to see that both of them, they go to the same direction. Unlike here, they are going similarly, but the thing is, this one is going down and this one is going up. You understand that? So that's how you know it's concentration, including a spike. Ne? But for temperature here now, how you're gonna see that is temperature the factor, you will see by these by the fact that both of them are gonna go, they're gonna have spikes. It's like both of them are gonna have spikes, yeah, but one is gonna have a larger spike compared to the other. Okay, so now the one that will have the largest spike, the one that will have the largest spike is gonna be the endothermic reaction. So as you can see here, they told you that enthalpy is 0. This enthalpy is 0, guys. It tells you that the forward reaction, is what? Is exo. If the forward reaction is exo, then what is the reverse reaction? The reverse, it means it's endo. So that is why the reverse is the one that increases compared to the forward, you see. So the reverse, remember, still this is the reverse here, and then this is the forward here, because we're dealing with reaction rate graphs. So as you can see, the reverse reaction is the one that becomes higher, and then it's gonna decrease, and then they form a new equilibrium. So that's what you must remember. But what will tell you that is temperature is the fact that both of them are gonna have kind of like a spike. You see, both have a spike, but the one that is going to have the largest spike is the reaction that was favored. Similarly here, you can see that both of them have a spike and it's going down. This was due to a decrease in temperature. Now we know decrease in temperature favors the exothermic reaction. In this case, our forward reaction is the one that is exo. That is why here the forward reaction, I want you to see that the reverse reaction now decreases more compared to the forward reaction, right? The rate of the forward of the reverse decreases more, right? So how can we interpret that? It usually makes sense if we're going up like this to say, no, the one that is going to be here is the one that will have a higher reaction rate. But similarly here, I want you to see that the solid line represents the forward. The solid line represents the forward. If it is higher like this compared to the dotted line, which is the reverse, which one is at a higher reaction rate? It's not the reverse, guys. It's the forward. You must be careful there. It's reaction rate. The one that is higher here, that is higher, is the forward reaction, while the reverse is lower, is at a lower rate. Why is that? Because the forward reaction was favored, because decrease in temperature favors the exothermic reaction, which is the forward reaction in this case. You see? So that's how you must check it out there. So understand that the one that will have a higher rate, when I just keep in mind which one will have higher rate by looking at your enthalpy there. Okay, just keep in mind that. Let's keep in mind that. All right, and then this last one. So if you change pressure, remember that an increase in pressure is gonna favor the reaction that produces a less amount of moles, meaning here we're gonna favor the forward reaction if we increase pressure. If we decrease pressure, we favor the reaction that's gonna produce more number of moles, which is the reverse. Now I want you to see here that it has the same effect as concentration. If you, for example, here if you increase pressure, remember, increasing pressure means you decrease the volume because they are inversely proportional. So if you increase pressure, we're gonna favor which reaction? The forward. Guys, what is important is for you to just ask yourself for which reaction is gonna be favored. So it's the forward reaction. That's why you see the forward reaction is spiking up like this, okay? But both of them, they also go up, but then they gradually decrease. It's more like similar to temperature. Do you see that? But it's different in this form. It's different in that for temperature, the reverse is the one that was favored here. But here, the forward is the one that was favored because the forward produces less number of moles. Then similarly, if you decrease pressure there, which reaction are you going to favor? You're going to favor the reverse, and that is why since we favored the reverse, you see that's why the reverse is at the top. So what I want you to understand, maybe for all of these red graphs, so that you don't get lost, because they can become a bit confusing. I don't even want to lie to you guys. These things, they were like hell when we were at school. But then let me just give you what to maybe look out for there. I just want you to understand the following. If you see one spike, and then this one is gradually increasing like this, since there is one spike, there is one reaction that spiked, that means you changed concentration. Okay, it means you changed concentration. And then the one that is at the top there is the reaction that was favored, right? So the one at the top is the reaction that was favored. Now if you see something like this, and then you see this, then guys, this one means it can either be temperature or pressure that was changed. Okay, but you must know that the one at the top is the reaction that was favored. Are we okay here, guys? The one that is at the top, what do I mean about the one that is at the top? Let me highlight it. When I'm saying the one at the top, I'm saying this one. Oh guys, let me use blue then, or green. I'm saying this one is the one that was favored. Is the one that was favored here. This one is the one that was favored. Right. Are we understanding there? If we understand it this way, guys, you're okay with rate versus time graphs. If you understand it there, you are very much okay. That's all you need to know. That's all you need to know. Right. So that is what is happening there, That is what is happening. Now, if we turn the tables around, I'm still gonna have the similar graphs I'm still gonna talk about a rate graph versus time. So this is gonna still be a rate. However, now I want to show you this. Let's say we have reached our first equilibrium here, and then I want to do this. It's not that beautiful, guys, but I want it to be visible. Let's try doing this. Let me do this. So this one just comes along like this. Now guys, if you see something like this, if you see something like this, because there is one spike, it is still concentration. Because there is one spike, it is still what? Concentration that was favored. Concentration that was changed. That is the factor. Then which reaction was favored? Guys, please understand the following now. Which reaction was favored? Let's go back here. do you remember that I said to you, if you remove NO2, then you're gonna favor the reverse. Ne? You're gonna favor the reverse. And then I want you to check something. I want you to check here. The reverse was at the top, isn't it? Now, here's the trick that you can use, or rather, here's what you can just understand about it. The one that is at the top here, is the one that was favored. Ne? It is not this one that is going down, down, down. The one that is going down, down, down was not favored. You feel me? The one that is going down, down there, it was not the one that was favored. The one at the top is the one that was favored. Okay? Understand it that way. Now, if we reach the equilibrium, and then we see both of them, they go down. Oh, my dear. And then it comes back, and then this one, it gradually just, does this and reach equilibrium. The one that is at the top is the one that was favored. Okay, so favored, let me highlight it with green. This is the favored one, this is the favored one. Alright, if they are facing down like this, the one that is at the top is the one that was favored. And now, what factor was changed? Here we said it's concentration because it's one spike, but here because we must start with two spikes. I think I made a mistake. Yeah, I made a mistake there. It must be two spikes. Just that is difficult to show. But then two spikes, guys, and then it goes like this. So let me remove some of these. Now it wants to remove everything. Okay, what I was saying is that if both of them spike, like this, spike like this, and then this one does this, and then that one also does this, so what I'm saying is that this one is the one that was favored, but the factor here could be temperature or it could be pressure, because both of them have spiked. Both have spikes. That is it. Okay, so the one that will be at the top there is the one that was favored. The one that is not favored, it must go down, down, down. That's how you remember it, And if both have spikes, it means it's temperature or pressure. If it has one spike and the other one doesn't have spike, it gradually decrease, then it means that is concentration there. Okay, I hope that we understand how to interpret rate graphs. I hope we understand how to interpret rate graphs. Rate graphs, to conclude again, or rather to just close the chapter on rate graphs. Rate graphs, you just check the y-axis. What you do is that you check the y-axis. If your y-axis is the rate, immediately in your mind you must think about forward reaction, and then you must think about reverse reaction. Okay, and therefore you will be able to answer the questions there. So we also have what you call concentration versus time graphs. Guys, when you have concentration versus time graphs, what you should think about is that I'm going to be visualizing the individual reactants that are on the question. For example, A plus B, right, give me C plus D. When I'm saying concentration versus time, I should remember that I'm talking about the concentration of either this one or that one or that or that. I'm showing their concentrations in real time. So which means that here I will have the graph like this. This will be time here, and then this will be the concentration. So for A, right, and let's remember that for concentration time graphs, they're telling us that here the reactants, they should be decreasing while the products should be increasing. Okay, So because it's like that, when you draw the graph for A, it's gonna be like this. This will be for A. Then for B, it's gonna be like this, because they are decreasing. But then the graph for C and D is gonna be like this. Now you never know, they might even cross and then like that. So this is C, this is D. Then there is this time here, which will be maybe T1, that they reach equilibrium. This is equilibrium number 1. Okay, it's equilibrium number 1. They don't have to touch each other, because it just shows that you had this amount of D at equilibrium, you had this amount of C at equilibrium, you had this amount of B at equilibrium. Just like we were doing the Kc calculations, remember they were telling us that at equilibrium you have the concentration of B to be this, to be that. That concentration, now we are just reading it on the graph itself. You'll be able to read it on the graph here. Okay, so that's why Kc calculations, they can also ask them in terms of graphs. Now if you increase the concentration of one of the reactants, guys, if you increase concentration, you will see by a spike. Okay, so A is gonna go up, right? That means you increased A. No. Oh yeah, you increased A. Since you increased A, guys, what will the system do? The system is gonna favor a reaction that is gonna oppose that. So that means that A will start to get used up. B will also start to get what? Used up. You see? And then what will happen to C and D? C are going to start to increase. D is going to start to increase, and then they reach another equilibrium. So this is equilibrium number 2 here at T2. So it's equilibrium number 2. Then it goes on like that, guys. If you decide to remove C, let's say you remove C, you will see by the spike, then the reaction, the system is gonna favor the reaction that will increase C, because you removed it again. So the reaction that increase C, it's gonna be what? It's gonna be the forward reaction. So which means now that A and B are gonna start to get used up, while C is gonna start to increase, and then D is also gonna start to increase. Then you reach another equilibrium. This is T number 3. You understand? So this is equilibrium number 3. So guys, it's all about, if you in concentration, it's all about if you increase this one, what will the system do? Once you understand which reaction is going to be favored by the system, then you will know which ones are going to decrease, you will know which ones are going to increase. The spike, right? The spike tells you the concentration of the one that was increased or decreased. So the spike represents the concentration of that thing that you increased or decreased. Okay, if the spike is going up, it means you increased something there. If the spike is going down, you decrease something. So that is how you interpret concentration versus time graphs. They tell you about the individual compounds or molecules or elements. Okay, while the rate versus time graphs, they are talking just about the forward reaction and the reverse reaction. Whether it doesn't really show the reaction rate graph, they don't show you we increased A or we increased B. You see, it doesn't really show that. It only shows you that what the reactions are doing, the reverse and the forward, while concentration shows you clearly which one was increased, which one was decreased. Okay guys, I hope that is clear. And then you can just try to do questions on this, see what is going on there. Then you get to understand, or why are those graphs like that. If I have a concentration versus time graph, right, then maybe I had 2A plus maybe B2 giving us 2AB. So if you had this and then this is the concentration versus time graph. Ne? If you increase pressure, which reaction is going to be favored? The one with less molecules. So we're going to favor the forward reaction. So what will happen is that initially A is going to be like this, B is going to be like this, and then AB is going to be like this. They reach equilibrium. So this is A, B, and AB. Now, if you disturb the equilibrium by increasing pressure, these two, you have favored the forward, these two are going to sharply decrease. So A is going to decrease, B is also going to decrease, right? And then what will AB do? AB is going to increase. Then they're gonna also do like this, and then it's also gonna do like that. Then you're gonna reach another equilibrium. So how will you will see that it was pressure if both of them are gonna sharply decrease or sharply increase. You understand? If both of them are gonna sharply increase or sharply decrease, you know it's pressure. If one of them only has one spike, then you know that it's concentration. Well, if there is no spike at all, if there is no spike in a concentration versus time graph, then it is temperature that was changed. Okay, it is temperature that was either increased or it was decreased. Okay, if there is no spike, it is temperature. If there is two spikes, then it is pressure. Then if it is one spike, it's concentration that was changed. Okay, then yeah, then in terms of these graphs, I hope that we understand them there. Okay, so try these on previous papers there and see how far you're doing. I'll probably send you some question papers that you can try, and then I would really like it if you can send to me. No, right, just answer, then you send to me. We mark each other as we go, and if I see that most of you are still not getting this correct, we will still talk about more of equilibrium. Okay, so any question? Okay, no problem then. See you soon, and have a good night.